Good morning, good afternoon, good evening. Welcome to another session of my presentation series, and this time the topic is special testing of power transformers. My good name is John Kweko Amuotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Now, let's talk about this. If you watch my video and basically you like it, don't forget to select the like button as shown over here. That shows a thumbs up. Then share with your friends. And don't forget to subscribe to my channel shown below. This is the name of my channel, Work and Happiness, talking to the engineer in YouTube. There are a lot of learning and presentation materials in this channel for your career enhancement and your career growth. Now let's talk about a special test that can be performed on a power transformer. And the first one is a zero sequence impedance, right? And zero sequence impedance is shown by Z0. And what is the purpose of the zero sequence impedance? Okay, so if the protection relay engineer wants to perform and determine the impedance of the transformer to set a protected relay, and based on single line to ground fault, double line to ground fault, then it becomes important that basically the customer will request for the zero sequence impedance parameter of the transformer. As you know, to determine the sequence current, basically the path for single line to ground fault is shown by Z1, Z2 plus Z0, right, divided by V. Right, so this is the positive sequence impedance for the transformer, and that is equivalent to the nameplate impedance. And this is the negative sequence impedance, and this is the zero sequence impedance. And you have, let's say, if you have a transformer where the Y side is grounded through a resistor, then that becomes the 3ZN, right? So this becomes the grounding impedance that is in the path of the Y side of the transformer. So if this is the grounding impedance or grounding resistor from the Y side of the transformer, this is 3 times this value, right? This is shown over here. So that is how the sequence currents are found based on a single line to ground fault. So that is the reason why the customer will request for such a special test to help the protected relay engineer perform his settings, and basically based on him being able to calculate the fault current that occurs due to a single line to ground fault and a double line to ground fault. Another special test, right, is short circuit test or withstand capability, right? Okay, so this can also be classified as a design test or type test, right? But when a customer wants to see this test for himself, wants to witness this test, then that is when he can request for this test, which also can be classified as a design or a type test. Right? Okay, so the short circuit test, what do we do, right? Okay, you have the high voltage side of the transformer, you have the low voltage side, right? These are the terminals, right? Phase A, phase B, phase C. Phase A, phase B, phase C, right? Okay. So the low voltage side is short circuited, right? This is short circuited. And a rated voltage is applied to the high voltage side, let's say 8% of the voltage, to let's say 15% of the voltage, of the rated voltage of the high voltage side. Let's say if this one is 230 kV, right? So 10% of 230 kV is applied to the high voltage side until the rated current on the low voltage side is achieved. So during this test, right, the power transformer should be able to withstand this short circuit capability without any degradation, any performance failure, right, without it catching fire, right? So this is what they call short circuit withstand capability test. At the same time, during the test, right, the copper losses, I squared R, or the load loss, is measured utilizing the voltage measurement, the current measurements, the voltmeter, the ammeter measurements, and also you can have a wattmeter that is in phase A and phase C for those measurements. So all these measurements are put together to basically obtain the total load loss. Then the load loss is added to the no load loss to get the total loss for the transformer. Then this is utilized in the temperature rise test. Okay, so this is what short circuit test or withstand capability test means. Next is harmonic contents of the no load current, right? Okay, so let's take a look at the equivalent circuit of the power transformer, right? Okay, you have a resistance, you have a reactance, then you have a magnetization branch, which consists of a resistor and a reactor in parallel. Then you have the high voltage side of the transformer, you have the core. Then on this side, you have the low voltage side. Then on the low voltage side, you have the resistor, the reactor, and the load. Right? Okay. So this path is your magnetization current, right? The I0. Then on this part is your magnetization current that has been broken into two parallel paths, right? One part that goes is the resistive part, and the other part is the reactive part of the current, right? Okay, so you have I current flowing here. You have a resistor, you have a reactance or an inductor here. Okay, so this is the primary side resistor, primary side, and this is the secondary side resistor, then secondary side reactance. Okay, so you have a voltage that has been applied over here, right? Okay, so during energization of the transformer, right, if you apply a voltage here, you have current that is going to flow, right? Okay, so the current is going to basically set up a magnetic field in the core. This is the core part of the transformer, right? The core. Let me draw the core for you. Right? So the path that goes over here, this is the magnetic part of the transformer. Okay, so during energization of the transformer, right, with this, the secondary side not connected to a load, right? So the differential relay will see this as a fault condition because current is flowing here, primary current is flowing here, and this secondary current is zero because there's no load connected. So the differential relay will sense it as a fault condition and trip the transformer during energization of the transformer. So our goal is to prevent such a phenomenon, right? To help the transformer to ride through the energization series. So what do we do? So that is the reason why the protected relay engineer or the customer requests for the harmonic content of the no load current. This no load current, as you can see over here, is rich in harmonics. The second harmonic, the fourth harmonic, and the third harmonic, and the fifth harmonic. So we can utilize the richness of the harmonic content in the second harmonic, the fourth harmonic, and the third harmonic, and the fifth harmonic to differentiate between an inrush current condition and a true fault condition, because a true fault condition has a lower amount of second harmonic current and fourth harmonic current. So based on this, we can distinguish between the two, right? Between an inrush condition during energization and a true fault condition. So that is the reason why the customer requests for this harmonic content of no load current. So the testing is done, and utilizing a power quality meter, these percentages are determined and provided to the protected relay engineer to be able to set the second harmonic blocking inhibits and the fourth harmonic blocking as a percentage of the fundamental frequency F1, right? So that the transformer can ride through this energization series where the significant amount of magnetic inrush current it can be up to about 12 times, and sometimes depending on the size of the transformer it can be up to about 30 times, and sometimes based on the amount of residual flux due to the time on the sinusoidal wave that the power transformer was de-energized. When the circuit breaker basically opened, the amount of residual flux that is embedded in the core, based on that amount, sometimes you can see up to 30 times the full load current as your magnetic inrush current. So that is the reason why we do this one as a special test, and the results are provided to the customer and the protected relay engineer. Next is a functional test of the pressure relief device, right? Okay, so the pressure relief device is a device that is mounted on top of the transformer, right? Its ANSI designation is 63X or 63, right? Okay, so it is the last resort of protection for the transformer, and this is the reason why. Okay, the main protection scheme for the transformer is differential relay, right? You have a differential relay that protects the transformer as the main protection unit, right? If the differential relay should fail, then you have a backup protection 50-51 relay that basically will pick up and trip the transformer. On the other hand, too, you have the 63 sudden pressure relay that basically can be the first time protection scheme for the transformer if the differential current has not developed enough current for the differential relay. So that is when the 63X, the sudden pressure relay, basically picks up and trips the transformer on very small magnitude of faults, 10 to 10 faults, strand faults, that basically creates a small pressure wave. So if all these protection devices fail, right, then that is when the pressure relief device basically comes into play. Because that time there would have been, the fault would have evolved to a bigger pressure, and there's a lot of pressure wave inside the transformer, and that pressure has to be expunged, has to be relieved, right? So this pressure relief device has a set point, let's say 10 psi, right, based on the amount of pressure, right? The worst case short circuit current is calculated, right, based on the impedance of the transformer, right? And the time duration of all these protected relay devices are failing, based on that electromagnetic force is determined, and based on that the pressure equivalent to the electrodynamic force is determined. and so this determines the set point of this pressure relief device. So when all these protective relay elements fails, then that is when the pressure relay device opens up and expunges all the oil onto the floor. So testing is done. Functional testing is done basically to determine and validate the set points of the pressure relay device. Same thing with a Buchholz device, right? Okay, so the Buchholz device is implemented for open concentrator tank, free breathing transformers, right? Where you have a concentrator tank, right? And you have a main tank over here. Then you have basically a downcomer piping, and in between the piping from this concentrator tank, which is basically a reservoir, and this one is the main tank, right? You have the Buchholz device here, protective relay device, and it has three functions. Its function is to trip the transformer based on low oil level, or alarm based on low oil level, or trip the transformer when you have basically a true fault that comes in, an extent of true fault on the low voltage side. Basically that causes a true fault current to flow through, and basically that just creates a pressure wave that goes through the piping and flows backwards and hits a vein that is here and trips the transformer. Another function is basically incipient gassing, right? Due to broken connections, due to broken strands, right? Due to broken 10-to-10 shorts, right? That creates gassing, right? Settling gassing, for example, basically that rises up and collects into a chamber, and based on the volume of gassing, basically it activates a switch, and basically it provides a alarm, right? So that is the Buchholz device. And next is the sudden pressure relay, and I explained the sudden pressure relay. Usually it is mounted on the sides of the transformer tank, right? And it can be the first line of defense of protection for the transformer before the differential relay, based on the magnitude of the fault current. If the magnitude of the fault current is so small, then the sudden pressure relay can be the first line of protection for the transformer, right? If the differential current is greater, then basically the differential also picks up. On the other hand, if you have a true fault, right, basically that creates a pressure wave, then the sudden pressure relay can see that magnitude of a true fault and can trip, right? But in addition, if you have an internal fault that basically has a lower magnitude of fault current, then the sudden pressure relay can pick up. Next is acoustic sound level, right? Okay, in dB, right? Okay, so this is an application. Sometimes certain transformers need to be installed in certain facilities, certain neighborhoods, right, where noise compliance is very, very important, right? Okay, and also based on the city ordinance, there's a requirement for sound level to be complied and maintained, right? Okay, so that is when the customer requests for that specific sound level criteria, not greater than that, to be met during the design of the transformer, right? So determining the sound level of the transformer is all based on the core of the transformer, right? The core material, the material of the core, and the arrangement of the core material, the laminations. Because if you have the flux that is traversing the path of the core laminations, that is where it creates that noise, right? It's called chattering noise. Okay? So it's all based on the type of core material, the laminations, the arrangement of the laminations, and also basically clamping of the laminations tightly, right, to prevent that chattering noise. And also the fans, basically, the fans dB, the amount of dB that is exhibited by the fans and the pumps. All these add up to the total acoustic sound level. And also the eddy currents and hysteresis current that is flowing through the conductor also creates audible noise. And also the leakage flux that basically impinges inside the tank walls of the transformer also creates a little bit of audible noise. So these are all the sources of the sound level that is determined during design. And during acceptance testing, this testing is done to make sure that the transformer that is leaving the factory floor meets the design criteria that is needed by the customer. Next is the power taken by the fans and the pumps, right? Okay, so you have the fans that are mounted on the radiator peripherals, right? You have the pumps that are located below the piping coming from the bottom of the radiator, then comes to the bottom of basically, the transformer, right? Okay, so the cooler oil comes from the bottom through the pump, and the pump pumps it. Okay, so the purpose of the pump is basically to push the oil as fast as possible to remove the heat that is generated by the winding, and basically to maintain the temperature rise, the oil temperature rise, and the ambient temperature rise within design criteria, right? Okay, so, and also the fans, right? The fans are mounted on the peripheral of the radiator walls, also to remove the heat, right, on the thin surface of the radiator. Okay, so the power that is taken from the fans and the pumps can be requested by the customer, right? When you can ask yourself, what is the reason why the customer is asking that? Okay, these fans and the pumps are fed from an auxiliary voltage source, right? Let's say 480 volts MCC, right? Okay, and the sizing of the breaker, right, has to be determined, and the amount of, based on the worst case amount of current that these auxiliary feeders are going to provide, right? Okay, so that is why we do that testing and provides that results for the customer, so that the customer can determine where to feed the power from my motor control center to these fans and the pumps, right? Okay, so the last one is the special dielectric test, and the special dielectric test is the dielectric frequency response, right? Okay, so this one is basically where basically it's a frequency range, right? Where basically from millihertz to, or let's say kilohertz to megahertz, and the power factor of the paper insulation and the oil insulation is determined, right? So it just gives you the plot of that, and the customer can request for that as a fingerprint for their transformer, so that in the future, if they want to basically determine the amount of moisture in or contamination level in the oil and the paper, they can utilize that as a fingerprint. With that comes to the end of my presentation, and look out for a more series of presentation, and don't forget to select the like button if you like my presentation, or select the subscribe button, and you can also visit my YouTube channel, and there's a lot of tons of presentation and material for your learning curve and for development of your career. With that, thank you.